So far, we discussed work done by a constant force. The force does not change with time. And only then will our simple definition of work will work. Now, what is the simple definition of work? Work done equal to force multiplied by the displacement. This will work only if this force remains a constant. Now, very often, the force may not remain a constant. For example, I want to stretch this spring. Now, if I want to stretch a spring, if I apply a force on the spring will stretch. If I want to stretch it more, I need to apply a greater force. See that? Now, what you notice here, that the amount of stretch is proportional to the stretching force. Do you notice that? If I apply a greater force, the stretch will be greater. In other words, the force here varies with the displacement. Greater the displacement, greater is the force. I can write it like this. Force is directly proportional to the displacement. Well, here the force does not remain a constant. Force varies when the displacement varies. So we cannot use the simple concept. But we can actually extrapolate the result from here into the case where the force remains or the force varies. Now, what will be, in the first case, what will be the shape of a graph of force against displacement? If I draw a graph of force on the vertical axis and displacement on the horizontal axis, in the first case, when the force remains a constant, means the force will be a horizontal line. Now, what is the area enclosed by this graph with the displacement axis? What is this area? Well, the length of this rectangle is x and the width of the rectangle is f, is that right? And so the area of this rectangle is f multiplied by x, which is a measure of the work done. Now, this is actually a general result. If you draw a graph of force versus displacement and you measure the area under that graph, that will be a measure of the work done by that force. Now, can you extend that in this case? Yes, actually, you can extend that in all such cases, and we will talk about that as we move on. If the force F continuously changes, you could probably get a graph like this: displacement, force against displacement. Now, we have a neat way to interpret this. Now, consider a small displacement ds here, and when the displacement is very small, we can imagine during that displacement that the force F will remain a constant. And therefore, the work done for this very small displacement can be written as dW equal to force, this force multiplied by that small displacement. And we can do that all over under this graph and then add up all those small dW's. That will give you the work done. In other words, simply stated, no matter how the force changes with time, if you have the graph of force versus displacement, the area under that graph will be a measure of the work done. I want you to understand that concept. No matter how the force changes with time, whether it remains a constant or whether the force changes with time, if there is a graph available with force on the vertical axis and displacement on the horizontal axis, the area enclosed by that graph with the horizontal axis will be a measure of the work done. We will use that as we move on. Areas where we will consider force varies with displacement is actually the case of a spring. Alright, let's consider a spring. The figure shows a spring fixed to a support. And if you want to compress that spring, you need to apply a force. A force F applied at the free end compresses the spring by a distance dx. So let this force be x, and as a result of that x, the spring now gets compressed by a distance dx. You can see this force compressed this spring by a distance dx. Now, in order to compress the spring further, we need to actually increase the force. That means as the compression increases, the force needed to compress it further needs to be greater. Now, how do you write that? A greater displacement x requires a greater force F. And that means we say the force F is proportional to the displacement x. Now, whether the spring is compressed or stretched, this is the same case. If I want to stretch a spring, if I want to stretch it more, I should be applying more force. I increase the force in order to increase the stretch. The amount of stretch is proportional to the force, or the stretch is proportional to the force. Now, how do you write that mathematically? The stretching force is directly proportional to the force. F is directly proportional to x. And the proportional sign can now be replaced by an equal sign. F equal to kx. Now, this is called Hooke's law, where a spring, when applied either a compressing force or a stretching force, the amount of force is proportional to the amount of stretch, or F equal to kx. This constant is called the spring constant. So, tell me now, if I want to draw a graph of F on the vertical axis and x on the horizontal axis, what kind of graph will that be? Well, that graph will look like this. If I draw a graph of the force F on the vertical axis and displacement on the horizontal axis, it will be a straight line through the origin. Now, what will be the slope of this graph? The slope of this graph will be k, the spring constant. Alright, now tell me, if I measure the area under this graph, what will that area give me? The area under the graph will give me the work done by this force in producing a certain displacement x. Alright, let's measure that area. Suppose the displacement is x up to here, and we say this is my displacement x. That means this area is a measure of the work done. Work done therefore is, can you write what that will be? What is the area of this figure? Area under this graph. This is a triangle. The area is 1/2 base multiplied by the height. What is the base of this triangle? It's the displacement x. What is the height? Height is the force. So work done is given by the area enclosed by the graph of F against x. And that will be the area of the triangle. That will be 1/2 base times the force F. Alright, help me rewrite this. This F, if you know, is given by the Hooke's law, F equal to kx. So in here, I'm going to replace that F by kx. And let's see what the equation now becomes. That will be 1/2 x times kx. And that will be 1/2 kx squared. A very important relation. In the case of a spring, if you want to stretch the spring by an amount x, the amount of work done is W equal to 1/2 kx squared. Alright, so if I want to stretch this spring, now this is the length of the spring when it is not applied any external force. If I now apply a force on it, I'm going to stretch this by suspending this weight from there. Now tell me, what is the stretching force if I suspend this mass? The stretching force will be mg. I have now produced an amount of stretch x. Now look at this. This is the length when it is unstretched. Now I can measure the length x, and therefore I can now calculate the work done in producing the stretch. What is the work done? Equal to 1/2 kx squared, where k is called the spring constant of the spring, and x is the amount of stretch. Okay, tell me, what is the unit for measuring the spring constant? K. K will be measured, if you solve for K, you can see K equal to F over X. That would be Newton per meter. K is Newton per meter. It is a measure of the amount of force that is needed to stretch the spring by 1 meter. That is the value of K. Suppose I say the value of K for this spring is 30 Newton per meter. It means if you want to stretch this by 1 meter, I need to apply a force of 30 Newton. That is the meaning there. So what this shows is that the work done in stretching a spring by a distance x equal to 1/2 kx squared. The work done in stretching or compressing, both remains the same. Let's start with this problem. A particular spring has a force constant of 2.5 times 10 to the 3 Newton per meter. How much work is done in stretching the relaxed spring 6 centimeter? Well, the relaxed spring means your x1 equal to 0. You got to stretch the spring by a distance x equal to 6 centimeter. Well, straightforward, is that right? And how much work is done in stretching the spring an additional 2 centimeter? All right, let's put down the values we know. The force involved in stretching the spring is identical to the force required in compressing it. So we will use one for the other without any problem. In part A, the spring is stretched from an initial position x1 equal to 0. It's a relaxed position. To x2 equal to 0.06 meter. So x1 equal to 0, a force F stretches it to x2 equal to 0.06. So it is this displacement that we call 0.06. Work done is 1/2 k x2 squared minus x1 squared, where your x1 equal to 0. And you use all the values. K is given to us, and x2 we know, x1 we know. That is 4.5 joules. Alright. Next, how much work is done in stretching the spring an additional 2 centimeter? Well, the spring is now stretched from x2 equal to 0.06 to x3 equal to 0.08. That means it is now stretched from x2 equal to 0.06 to x3 equal to 0.08. Now, therefore, work done will be 1/2 k x3 squared minus x2 squared. And now use all the known values. x3 is 0.08, x2 is 0.06, and that gives you 3.5 joules. You can see the additional work needed to stretch it by this much is much greater than the initial work. That means as you keep stretching the spring, the amount of work you need to do to stretch the spring by the same amount keep on increasing. Why? Because the force keeps on increasing. Another one. A student suspends, now do another problem. A student suspends a 0.25 kilogram mass on a spring and it stretches a distance of 5 centimeter to its equilibrium position. The student then pulls down the suspended mass, doing 6 joules of work in further stretching the spring. How far is the spring stretched as a result of the pulling down by the student? Well, what we have is the case of a spring and the student suspends a mass. Now, what is the stretching force here? The stretching force is the weight of this mass. Alright, let's write that down. What is the weight of the mass? The mass is 0.25 kilogram. So its weight will be 2.45 Newton. Now, this 2.45 Newton stretched the spring by how much? The 2.45 Newton stretched it by 5 centimeter. What does it help you to find? Now, you know that the stretching force F equal to kx. This helps us to find the value of k of the spring. You see, in the problem we need the value of k. So let's find the value of k. The displacement produced by this force is 0.05 meter. This is the relaxed spring. And now when we suspend a mass or applying a force of 2.5 Newton produces a displacement x equal to 0.05 meter. Therefore k, remember, F equal to kx or k equal to F over x. F is 2.4 Newton, x equal to 0.05 meter, and therefore the k value for this spring is 49 Newton per meter. So the first part of the problem helped us to find k. Alright, let's now take the second part. From the equilibrium position, the spring is stretched a distance x in doing an amount of work W equal to 6 joules. Well, if this is the equilibrium position, now we're going to say x equal to 0 now, and the student applies a force doing a certain amount of work. How much? 6 joules of work in stretching the spring. We need to find how much is the spring stretched from this equilibrium position so that that amount of work, 6 joules, is done. Alright? We know the work, we need to find the distance x. So the student does an amount of work in stretching the spring by an additional distance x. Now W, the work done, equal to 1/2 kx squared. And we can now replace W by 6 joules. K is known, and therefore we can solve for x squared. X squared is 6 times 212 divided by 49. And that will give you x equal to 0.49 meter, which is 49 centimeter. Okay. Another problem. Compute the work done by the variable force F versus X graph shown below. That must be very simple because work done is a measure of the area enclosed by the graph of F versus X with the x-axis. But one thing you need to know to do this problem, and that is, if an area measured above the x-axis is positive, the area measured below the x-axis is negative. So there are two triangles here. The area of the triangle above the x-axis is positive. The area of the triangle below the x-axis is negative. Work done is given by the area enclosed by the graph of F with the x-axis. Now this area is made up of two triangles, one above the x-axis and the other below the x-axis. The area measured above the x-axis is positive and the area measured below the x-axis is negative. Let's measure these areas. What is the area of the first triangle? Well, area of a triangle is 1/2 base multiplied by height. Now what is the base here? Base is 2 meter. What is the height? The height there, this is 2, 4, 6. The height is 6 Newton. So that will be 1/2, base is 2 meter, height is 6 Newton. That will be 6 joules, that is positive. And area of the second triangle is, of course that would be negative, is that right? That will be 1/2, base is, what is the base? 5 minus 2 is the base. And what is the height? Now look at the height of the triangle. The height is negative 6. Negative 6. So that will be negative 9 joules. Okay. The area of the top triangle is positive 6 joules. The area of the bottom triangle is negative 9 joules. And therefore the total work done is the sum of the two. 6 joules minus 9 joules equal to negative 3 joules. Okay, let's now talk about another concept called power. What is the meaning of power? Very often children fight against each other saying, oh, I'm more powerful. Now, how do you judge the power of a person? Well, if two boys compete, we can say, all right, I want to see how long you take to jump upstairs. Now you got the stairs going up. So the first boy goes up. I time him. He takes 6 seconds. And the second one tries. He takes 8 seconds. Now, who is more powerful? You see, if a person is more powerful, that person can do the same amount of work in less amount of time. You see? So, how do we define power? Power is the rate of doing work. The rate at which work is done is called power. And you can calculate power as work done divided by the time taken. What is the unit for measuring power? Work is measured in joules. Time is measured in seconds. Therefore, power is measured in joules per second, and joules per second is called a watt, and we represent that by the uppercase W. Now, notice all these are very important concepts. So, what is the unit for measuring power? Power is the rate of doing work. It is measured in joules per second. And a joule per second is called a watt. So the unit of power is the watt. Tell me, you have a 60-watt bulb in your bedroom. What does that mean? 60 watt. It means that bulb will use up electrical energy at the rate of 60 joules per second. That is why it is called a 60-watt bulb. 100 watt is 1 kilowatt. Since power is the rate of doing work, we can say power is delta W divided by delta T, dW by dt, the rate of doing work. Power is the rate of doing work. You can also rewrite right from here without going through calculus. And that is power. Work done is force multiplied by the displacement. Divide that by time. And that will be force multiplied by x over t. What is x over t? Displacement divided by time is the average velocity. So force multiplied by average velocity is a measure of the average power. That will be force multiplied by velocity. These are very useful concepts. Average power is force multiplied by average velocity. Okay, we can actually use these concepts to solve problems. Let's do a small problem. A 1500 kilogram race car can go from 0 to 90 kilometers per hour in 5 seconds. What is the average power required to do this? Well, we have V0, initial velocity is 0. The final velocity is 90 kilometers per hour. Convert that to meter per second. Divide by 3.6. That gives you the final velocity is 25 meters per second. The time taken is 5 seconds. And the mass of the race car is 1500 kilograms. That is our data. First of all, we find acceleration. What is the acceleration caused by the force producing that acceleration? Acceleration is Vf minus V0 over t. And that gives you 5 meters per second squared. Now, if the acceleration is 5 meters per second squared, and this acceleration is produced on this mass of 1500 kilograms, therefore, can you calculate the force producing that acceleration? The force producing this acceleration is F equal to ma. That will be mass multiplied by the acceleration. That is 7,500 Newton. Now, this is the amount of force that is used in accelerating the car. The average velocity during this 5 seconds. Can you tell me what is the average velocity during this 5 seconds? Because the acceleration is a constant, the average velocity is simply initial velocity plus the final velocity divided by 2. So the average velocity is V0 plus Vf over 2. 0 plus 25 over 2, that is 12.5 meter per second. A force of 7,000 Newton applied on the car gave it an average velocity of 12.5 meter per second. Therefore, what is the average power required to do this? The average power is force multiplied by the average velocity. The average power is force multiplied by the average velocity. That will be 9.375 times 10 to the 4 watt, or which will be 93.75 kilowatt. All right, let's do another problem. A 1500 kilogram elevator accelerates upward at a constant rate of 0.5 meter per second squared. How much power is developed on an average during the time the elevator speed increases from 0.25 meter per second to 0.75 meter per second? Here again, we have the initial velocity, final velocity, we can find the average velocity. And we have the mass of the elevator, we have the acceleration of the elevator, we can calculate the force that is producing that acceleration on the elevator. First, we find the force required to produce this acceleration of 0.5 meter per second squared upward. Well, that's not difficult. F equal to, now you must understand that the force applied first has to overcome the weight of the elevator, which is downward, and then it has to produce the acceleration upward. Is that right? So the total force required to do that is F equal to mg plus ma. We have actually done that in a former lesson. In order that the elevator may be given an upward acceleration of 0.5 meter per second squared, first of all, the weight of the elevator need to be overcome. So you need to apply a force equal to the weight of the elevator first. Now, once that force is applying upward, the elevator is now ready to move up. And then the additional force required is mass times acceleration. So the total force that is needed to accelerate the elevator upward is mg plus ma. That is 15,450 Newton. It is this force that is doing the work in this case. The initial velocity is 0.25 meter per second. The final velocity is 0.75 meter per second. Therefore, the average velocity is V0 plus Vf over 2. That is 0.5 meter per second. And so, what is the power developed for this purpose? Power developed is the force multiplied by the average velocity. This is the force, this is the average velocity. Therefore, the average power is 7,725 watt, which is 7.725 kilowatt. I hope this concept of power connected to average velocity is clear to you now. What I will be the brief description of work and power? Well, always remember, when you listen to the lecture, consolidate that understanding by doing the homework. And only by doing the homework you will learn the concept. Alright, I will see you for the next lesson in this unit later on.